Greetings! I've got a joke for you. Don't worry, it's a good one. How does the biblical figure Moses prepare his coffee? How does the biblical figure Moses prepare his coffee? You ready for it? He brews it. You get it? He brews it. Moses, Hebrew. Is it funny? I know you think it's funny, don't you? No? Okay, well look. Fine. Admittedly, I may not be very good at helping you laugh, but hopefully I'm a little bit better at helping you learn. So what we're going to do is something fun in this video. I'm just going to show you guys how you can use Python, the object-oriented programming language, not the snakes, because I don't mess with those, to model the historic experiment of Heinrich Hertz, who in 1887 was one of the first to generate and detect electromagnetic waves in a laboratory. So this is a fun piece that has been taken from the upcoming online course called Quantum Physics for Serious Beginners, where we basically delve into all this stuff with quantum physics to teach you about that, but we also take some time and delve into some of these historic experiments, which ultimately help to pave the way for the development of quantum physics. All right, so if that sounds good, then let's roll up our sleeves and let's go ahead and see if we can figure out exactly why Hertz would go on and observe these little electrical sparks, which ultimately was the evidence of the creation and detection of electromagnetic waves in his laboratory as soon as he actually flipped down his electrical switch. All right, so if that sounds good to you, let's get to it. All right. Hertz was the first person to generate and detect an electromagnetic wave in his laboratory. And what he basically did, what we're looking at here is a diagram, that really, this is an actual photograph of something that he used in his laboratory. And what you're looking at is just a table. And on these tables, these are two, I think it was something like 30 centimeters. These are zinc spheres, and two zinc spheres here, and copper wires that run from this point on the sphere to the center here, correspondingly over here, and then smaller spheres which have a gap in between the two spheres. And this gap, is basically you then have air, nothing covering it up or sealing it up. So you have a gap that exists between the two smaller spheres, and then you have these two bigger spheres which extend towards the end. And then he took long electrical wires and basically connected them to points on this side and this side of these lines, and the lines were coiled, and there was also a large scale induction coil that was used. And we'll see in shortly that was intended to provide large inductance, and basically had a switch as well as a battery, a DC battery supply. And when you throw the switch, what was noticed was that you could actually generate a spark here, and there was, and as I mentioned, he's detected as well. So he used this type of receiver, which is a ring. And this ring actually has a coil wound around it to give it inductive properties. And in this region that's covered up by the sparks that you can see here, there was a controllable gap that was there in the basically receiver. And at about 1.5 meters away from this, actually in the direction perpendicular to the screen, this was placed. And you could see a spark and then another spark, coinciding with this spark, evidencing that whatever was created here, it propagated to the receiver, to the detector, and evidenced by the creation of a spark here. All right, so this was the experiment carried out by Hertz, and what it ended up being was a proof of the creation of electromagnetic waves, which can be made from a circuit and propagate into to some point in space, in particular to this receiver. And the evidence of it in this case was just a spark. So there was nothing really beyond just observing these sparks, which indicated the creation and the propagation of the electromagnetic wave. So that's what Hertz's experiment was. And now we can start to understand what's going on in this system, because if you just look, these are open spheres and which just act like open circuits here. So when Hertz connected the wires or the lines here and the lines on this side, and then in between them was basically a battery supply, an inductor, and a switch. So, and the fact that the gap that exists here, this is nothing more than a circuit that has an inductor and a capacitor. So, and then we have a switch, which means that, there's a little bit of some dynamic effect, in that when you throw the switch with a battery supply, this ends up introducing some dynamics into the circuit, which we're going to be discussing. And because of the presence of the inductor of the capacitor, we can actually understand what was taking place. So if we come over here to the right and representing in the simplest form an inductor capacitor circuit, we can basically write what's known as Kirchhoff's law, which says that basically we can sum up the voltage drops across this loop, and that has to always, sum to zero, and it just means of continuity of the charge. So we have a capacitor, we have an inductor. The voltage drop across an inductor is L times the time derivative of the current, di dt. And the voltage across a capacitor is the charge divided by the capacitance. So L di dt plus Q leads to this equation, which says that because I is the charge, is the derivative, I itself is the time derivative of the charge. So dq dt, d2q dt squared plus Q over LC is equal to zero in the simplest circuit that we're talking about. We're going to generalize this in just a moment. But to understand what we have here, we can just talk about what's known as the harmonic oscillator, which is this circuit. So this circuit actually is known to actually give rise to, regardless, I don't need to have any dynamical components going on here, but just by combining these, all I need to do is have a certain initial condition, and this circuit will naturally drive into oscillation. So, and that's evidenced by, that's what the harmonic oscillator describes. So let's talk about this a little bit more. So Hertz spark generator, we can model this system. And how can we model the system? So first, and let's finish our conversation about this overly simplified harmonic oscillator. The second derivative of Q with respect to T plus Q over LC can be written in this way. So dQ, the second derivative plus, and I'll call this omega squared times Q. Now, why do we choose omega to represent 1 over omega squared in particular, to represent 1 over LC? It's because it's well known what the solution to the equation of this form looks like. So imagine that Q was let's say that it was a sine of omega t function. You take the derivative of a sine function is cosine, but it has a one caveat that it's going to also pull out the derivative of the omega, which is the coefficient of the time. So sine of omega t, the derivative of that is going to be cosine omega t times omega. That's the first derivative of the sine function. And if you would take another derivative, you would get negative sine, which sine being the original function we started with. So the second derivative of sine is actually proportional to sine. It's negative omega squared times the sine. So this term actually ends up being negative omega squared times the sine. And this ends up being positive omega squared times the sine. So this sums to zero. So this is describing something that is harmonic. And the same thing is true for cosine. And so linear combinations of sine and cosine end up being the general solution to an equation that looks like this. And at the end of the day, as I said, and it's remarkable when you think about the physical system, we had nothing in the system that would trigger some type of dynamical behavior. But simply by combining an inductor and a capacitor, that designs a circuit that naturally behaves in an oscillatory fashion. And that's really what's remarkable about this. And this is at the root of it. This is why Hertz was able to generate electromagnetic waves. These waves had to be oscillating harmonically in time. And this is how he was able to achieve that in a conjunction with the way the system was designed. So, but we need to go a little bit further with this equation. So instead of just looking at the inductor and the capacitor, we can add to that the resistance in the line. So the resistance just adds the I times R. So that, because we divided everything by L, that gives us RL times dQ dt. And then we also have a voltage source in the line, which is that battery that was used. And it was just the DC. So this number here is just a constant. So Vn over L, and we get this equation, which is a generalization to this, but we can write it in a similar way. So we can write this equation in this form where we have 1 over tau, because it turns out that L divided by R is actually a unit of time. And so 1 over tau, where tau is defined as L over R, And then omega squared has the same definition. It's just 1 over omega or LC. So that means that the frequency omega is the 1 over the square root of LC. And this equals Vn over L. And this is the equation that we want to solve. If we can figure out what the solution to this is, we can start to understand how the charge is behaving in Hertz's circuit. And when we do that, then maybe we can understand how a spark or an electromagnetic wave, which would ultimately create a spark, could be generated by Hertz's setup. All right. So the exact solution to this, anytime you have a linear equation with constant coefficients, coefficient being 1 over tau, in this case is 1, and the coefficient omega squared, which is just a function of the parameters, L and C. So a differential equation with constant coefficients always has an exact solution, especially when the right-hand side is either 0 or a constant or has some analytic solution over here. Then the solution to this is also going to be analytic or exact. And so that solution can be worked out, and that's what I show you down here. So I've taken the time to work this solution out. And what you get when you solve this, because the general solution of this is actually a exponential to a power of I times, or actually I should say, it's really a times the exponential of a root 1 times time plus b times another exponential where there's another root 2 times time, and that those roots are solved by basically determining what's known as a characteristic equation, which defines a second order polynomial that is, it has a similar form to this. It would look like x squared plus 1 over tau x plus omega squared. That's the corresponding characteristic equation. We just need to find the roots to that equation, and those roots go into the exponential coefficients that form the solution of this equation. And when you do that, this alpha turns out to be the real part of that root, and this beta is the imaginary part of that root. And actually the root is plus or minus, so the real part is identical between them, and the other part, the imaginary part, is plus or minus so they're basically complex conjugates. So we have r over 2l, which we call alpha, and beta as 1/2 of the square root of a function that just depends on the parameters r, l, and c. And we can use these two parameters to calculate what's the phase, and the phase is equal to the inverse tan or the arctan of the ratio between beta divided by alpha. And then the charge, turns out the time dependence of the charge, which is the exact solution to this equation, is given by what you see at the bottom. Q of t is equal to the voltage times the capacitance times 1 minus the amplitude A times the exponential to the minus t over 2 tau sine of beta t plus phi, where again phi is that phase which we define up here. That amplitude A is equal to 1 over the sine of phase. That comes from boundary conditions. The boundary conditions in this problem are that the charge is equal to 0 as well as the current equals to 0 initially. And that's because Hertz had a switch in this circuit. And so he started from an open switch and then he would close the switch. And this is why we use the boundary conditions of initial Q and I starting out at 0. All right, so these need to correspond to the actual physical problem that you're solving. Okay, so now what we're going to do is we're going to actually make use of Python. We're going to go into Python and we're going to actually solve in just a moment. We're going to solve this equation that would enable us to actually start to look a little bit more deeply at what's going on in the physical system here. All right. And then we'll also, at some point, I'll incorporate this solution and we'll make a comparison between the numerical solution we're going to obtain and this exact solution which we worked out down here. Okay, so we'll do that in just a second. So let's talk about how we can formulate this equation so that we can go into Python and calculate the solution that we want. So first, let's rewrite this equation. So we have the second order differential equation which has this form. And let me rewrite this so that I take everything except for the second order derivative onto the right hand side. So when I do that, we get the second order derivative is just equal to minus 1 over tau dq dt minus omega squared plus the voltage in divided by L. So this is just a rewriting of our original differential equation. Now what I'm going to do is I'm going to define two variables. I'm going to call one variable x1, and that's going to be the charge, big Q. And they're going to define the derivative of Q with respect to time, which is actually the current, as x2. So we have x1 and x2, which correspond to big Q, and the time derivative of Q. Okay, so if I use those definitions, then I can take this equation, for example, and the second derivative of Q is really the first derivative of x2, because x2 is just dq dt. So this can be rewritten as dx2 dt is equal to what we have over here, which is minus 1 over tau. dq dt is x2. Again, looking at the definition, is x2 minus omega squared times q, which is x1 plus vn over L. And then the corresponding derivative of x1 with respect to t is actually just equal to x2, which is what we have here. We're just rewriting this equation. So dq dt, which is d of x1, is equal to x2. That's this second equation. So we actually have two equations. Now we've traded. What's significant here is that these are first order differential equations, where we started with a second order. So we trade one second order differential equation for two first order differential equations. So we've made this even trade, so there's no loss of information, but it has the advantage that we only have to worry about first order derivatives, and that's a little easier. And the price we pay for that is that we have to keep extra, information in our memory, which is, in this case, the derivative of x1. So we have x1 and x2 that we can solve for simultaneously. And when we do that, we get out of this pair of equations both the charge and the current simultaneously. All right, so I hope that makes sense. But this sets us up so we can start to calculate things the way we want to do it in Python. But we got one more step that we got to take before we can do that. And that is we want to actually take these derivatives here, derivative of x1 with respect to time, derivative of x2 with respect to time, and we're going to use what's known as a difference formula, which is just an approximation for writing this simple first order derivative dx dt. It's just x sub I minus x sub I minus 1 divided by delta t. So this is a numerical approximation to the derivative dx dt. So if I take a formula like this, now note that these subscripts here, this is not one as corresponding to like the charge and the current, but this just represents the corresponding moments of time. So this is at time ti, this is at time ti minus 1. So this delta in x divided by the delta in t is an approximation for dx dt. So we can take this approximation and substitute it both in this equation as well as this equation and rewrite these after we do that, and we get these two equations here, where x1 at the time t sub I, which corresponds to x sub I, is equal to x1 at t sub I minus 1 plus delta t times x2 at t. And these are all on the right side. The evaluations are done at the previous time step. So, for example, if I have the initial condition for both x1 and x2, which we have, that's the current and the charge, or the charge, I should say, this x1 is the charge and this is the current. Those initial values actually allow me to start my first update. Then I'll get this value, and then I'll get this value, and then I'll do the same thing and march through the time step, the time sequence, and get the values of x for all those values of time. So now we have a set of equations with numerical approximations that we can go into Python, and I can code these exactly and get the solution to x1 and x2. All right. So now we can go and do this in Python and start to look at what's going on in the physical system that was designed by Hertz in his laboratory. All right. So let's do that now in Python. Okay. So now we can start to code up what we want to do in Python, so we can look at the physical behavior of the circuit that was constructed by Hertz in his experiment, so we can get a better understanding of the physics of the system he was using. All right, so we're gonna generate a new script for this particular exercise, and so we're gonna come over here to our project, and we're going to create a new, and then we're gonna do Python file, and I'm gonna call this one Hertz lab. And of course, we're starting out with an empty script, and we're going to use, of course, a few packages that we're going to need in order to, facilitate or provide some support for this. So one of them is NumPy, and we already have it. It was something that we installed when we installed several packages before we did matplotlib. So this was one of the ones that we installed. So we're going to import that, and we're also going to use something called math. I think I might want to use that one. So it's actually a question mark. But import also the same matplotlib, because we're going to also do plots of the final data that we get. So we're going to do that, and let's call that PLT again. So the first thing that we'll do is we'll go ahead and set up our experimental constants, so which are all related to the circuit constant. So let's define V for the battery, and I'll give that a value of 0.5, or you can give it whatever, just give it some number around 1 or something like that. That's not too different from the other numbers we're going to use. So L, which is the inductance, is equal to, I'm going to give these a value of 1, and then the capacitance I'll also use a nice convenient number of 1, and then for the resistance, again, I'll also use a convenient number of 1. And remember, there was a parameter tau, which we also had, which 1 over tau or tau, but if we're going to call it tau, then tau was L divided by the resistance. So hopefully you remember that. And we also have our frequency, right? We have omega, and our frequency was 1. And we're going to be, remember, it was 1 over the square root of the inductance times the capacitance, so 1 over the square root of LC. So that's what we're going to be calculating here for our frequency. So that is square root. Function is accessed through numpy, so just np.sqrt, and we're going to pass in what we're going to take the square root of, which is just L times C. So that gives us our omega, and we have our tau. So this gives us, for the most part, and the other thing we want to do is define the length of time we want to capture data. So how many, how far out in time do we want to actually do our calculations? So I'm gonna actually choose a number that is a multiple of our frequency omega, because so we can calculate, let's say, a few periods, if you will, of omega. So I can choose a number. In fact, I can calculate the period of the time, of course, is 2 times and just pi divided by omega. This actually gives us the value of the actual period for the circuit. So we can calculate that number, and we can use that to calculate the final time that we want as a multiple of TP. So let's now look at the values for our time vector, which is, again, we're just really setting up things that are all inputs that are going to go into the calculations. So we're going to have a t minimum. That's going to be 0. We'll start, the initial time is going to be 0. And then we're also going to have, and let me get rid of the underscores, because it's just a little bit more efficient to not have them. So we're going to say t max. And this is where we want to use our period. So we want to have some multiple of our period. So let's go with 3 times our period, which is TP. All right. And then I want to define a number of points, which this is for time, how many timestamps, and we can do, however many. And there's different ways to construct, obviously, the vector of time. We're going to do it one particular way. So I'll basically define a beginning and an end point and how many time steps I want, and then I'm going to construct a vector based from that, the array from that. Okay, so let's go ahead and start first with, 10,000 points, or let's just do 1,000 for starters. And so we're going to need dt, because remember, we're assuming a constant dt. Every time step we take is going to be the same amount of time. So our dt, or our delta t, if you recall, is just going to we can just formulate that as basically t max minus t min, and it's going to be divided by the number of points minus 1. And this gives us the actual difference of time between each time step when we formulate it this way. And then we're going to take, we can actually create our vector of time, and that we can call it, the vector of time will be, we used this earlier, so we're going to be using this probably a lot throughout this course. So hopefully you remember this command. So it's len space from numpy. So, and we can, again, we just basically specify t min, t max, and also the number of points. And so that creates an array for us that allows us to do that. And then, let's see, here's another little, it's a caveat that I want to point out, and why I'm going to do it this way. So remember that we have an initial condition, and we're going to define those values shortly. But because we have an initial condition, in this vector that I'm defining these points, I'm actually going to construct a vector that I'm going to use in my loop that will be, it does not have the initial value of 0 in there because I already know the values there. Those are the initial conditions for the charge and for the current, which we have said is going to be 0. So we don't need to do any calculations at that particular instance of time. So I'm going to define this another vector, and this vector is just going to be really the same. It's going to be actually a subset of TV, and it's TV. And remember, the first index for a list or a vector, an array or a list in Python starts with 0. So instead of starting from 0, it's just going to be 1, and then we're going to go all the way to the length of TV. So this vector I'm just setting aside because I'm going to use this particular vector when we loop integrate from and shortly. Okay, so that's the first. So now I guess we can define. I'm going to put some notes here just to kind of help us stay a little bit formatted here. So this are our time parameters, and we can actually put that up here and bring all this together. So we have that. Now let's do the initial conditions. And those, forgive my horrible typos, so that we have x1 and x2. So let me just call that x1 sub 0, and we know that that's going to be 0. That's the charge. So this is the initial charge, Q. And then we have x2 sub 0, which we also are going to set equal to 0, and that's the current. All right, so now we have initial value set up. We can go ahead and initiate, or initialize, I should say, the vectors that we're going to use to store the data for x1 and x2. So we can do that by just saying that x1, the vector for our first variable, which we call x1, and we're going to just stuff in there our x1, 0 as our initial vector. So it already has, it'll have that value, and we'll do, of course, the same thing for the second variable, which is the current. So that's x2. So we're going to set that equal to x. The list right now just contains a single value, which is our initial condition. Okay, so yeah, I think that's enough for the initial conditions, and then we can kind of, so what we're going to do when I do the loop, so I can say for t, for example, because we're going to just loop through the time vector, for t in tv2, and we're going to, this is where, and all we have to do now is just basically do our updates according to the equations that we worked out in our slides that we were just talking about. We worked out an update formula for x2 and x1. So we're just going to code that up explicitly in this part, where it's doing it in the loop at each instance of time, and only starting at the second step because we already know the value in the previous step. Right, and the initial step, in this case, just the initial, and then every time we update the time, we will already have the updated value in the previous step. So that's what we're going to be doing. So let's first update. I'm going to call the update for 1, which corresponds to the update for x1, and that one, if you recall, is just going to be given by the x1v, and it's going to actually be the way we get the last value. We could, a simpler way to do that is actually, I'll do this way first. So the length of the vector of x1v, whatever it is going to be changing. So, but it's the most recent value. So the length of that, and then minus 1. And so this is just because we need to get the previous one. So we're at, let's say, the one, whatever the updated time, we need the previous one before. So not the last one, but the one just before that. Okay, so we're using, and that is the one that will be available. So let's say if there's one element in here, then this will be 1. The length of x was going to be 1 minus 1, which gives us 0, which gives us this first element. You see that's how that works. So every time we update, it'll just get whatever the latest value in the list is, the last one. It's going to give us that value by calculating it this way. So that's going to be part of it. And then we're going to basically add to it. Remember our dt times. Let's see. Our dt, we're going to multiply that, and then times, and then we have to put in here for x1, we're just going to put, remember that the update rule for that one just involves dt times x2. So all we have to do to get that is really, it's going to look like this, except for it's going to be the x2 value. So we'll place that there and update this, change this to say x2v, and the latest value for x2, and that multiplies by dt, and that updates the value that we're going to use to append to x1v. Okay, and then now we want to do a similar kind of thing for our other variable, which is x2. So I'll call that update 2, and update 2 is going to be, remember that is x2v. We're going to get the latest value plus delta t times some funky stuff that's going to go in parentheses here. So I'm just going to basically type that out, and that's going to, it all comes from the equation that we saw before. So it involves, and I can actually leave this number here, the variable we're going to, all right, so one of the numbers for, this is for x2. So the update for x2, it involved, if you recall, there was a minus 1 over tau. So let's include that. So minus 1 over tau, and that, if you recall, that multiplied by, that's just going to multiply by x2 value, which is the derivative of the charge. So that's going to be similar to this value. So we can actually use this number. So get some space here for readability. And so x2v, and this is basically part of, and we're going to have to add some more terms here, but this gives us just the values, the first term, I should say, contribution to that goes in parentheses for the update for variable 2. And then we also had, in addition to the 1 over tau term, we also had a term that was omega squared, if you remember, minus omega squared. And to do that, you actually type in something like this, and this gives us omega squared, and this multiplies by, if you recall, what does omega squared multiply by? And it multiplies by q. So q is x1. So we're going to actually have something that looks like this, but it'll be the value of x. It'll be x1's value, not x2. So we'll change that to say x1. And we have that term, and then we also, if you recall, we also had the inputs. So the input term, there was a contribution from the voltage, and that was just V, and that's going to be V bat divided by the inductance. If you recall, we had the inductance, the battery, whatever that is, divided by the value of the inductance. And I think that is all the contributions for x2 update. So we have x2 plus dt, and then that multiplies by the contributions from the omega squared term, from the 1 over tau term, and from the battery term, and then we're adding that to the term, the updating term, which involves x2, and I think that is it. And then all we need to do after we have these values is update or append x1v. So x1v vector is, we're just going to append, and that the value that gets appended here is going to be update 1. And then we'll do a similar thing for x2v, and this is going to be updated by the second value, x to update 2. All right, so that goes there, and then this will just basically update, and by the end of this calculation, we're going to actually have a vector of, or a list of update values that in the end is going to actually be, it should be the same size as our original time v vector, because we know the values of the initial condition. We're starting out with those already in there, and then we're just going to update everything up until from 1, or from the time after the initial condition up until the very end. And so that when we put it all together, it's going to be a vector that's the same size as our original TV vector. That's what we're aiming for. And so now I guess we can go ahead and do some, well, first let's run it. We can run it to see if it actually gives us any, any indications of some problems or errors. And all right, so we can just kind of, and we haven't, of course, we haven't done any plotting. So let's just run it first to see if we get any errors so that we can, all right, so if I run this, you see what I did? So I actually didn't do, I need to actually make sure I do the right click because it's the first time I'm running the script. And we did get an exit code of 0 and so now, because we already have MATLAB plot, so we can actually do, we can do PLT, just if you remember we're going to do plot. And then we want to plot TV. And then here we're going to do also the array, numpy array of, actually, let's try it first. We may get it. I think it may be okay here because we're going to do x1v, and let's see if we'll do a blue line for x1v, which gives us the charge. All right, and then we also need to do a show, call show method. Okay, so for plotting, so let's run this and see if we get what we want. Ooh, let's see. Aha. All right, this looks reasonable. So what we have is a curve that starts out at 0, and then it ramps up, and it comes back down, and then it seems to settle, and it's settling at a number of at the number of 0.5. Now, this is the Q1, which is the charge, and because it's the charge, it just turns out that the actual final charge is going to actually be equal to where it actually equilibrates. It's going to be equal to the V of the battery source multiplied by the capacitance. And since the capacitance is 1, we're just getting it equal to the actual initial of the battery. So that's why this is there. If I were to change, in this case, let's change the capacitance to, let's double it or something, and we'll see that this leads to a different value of where it equilibrates. All right, so now we got 1 instead of 0.1. All right, so these are just results of the parameter values that we've chosen, but we have something now that we're calculating that actually gives us what the charge is doing. Now let me we're going to also add to that. So in order to plot both of these together, what I'm going to do is actually assign. The way I can do that, an easy way to do that is I can basically write. I can actually store each plot, and that's what's great about the way this is set up, because this is how this doesn't actually plot it. What this does is it sends the data and assigns the data to an object, to a plot object, and calling this method on that object is what plots the data. So what we can do is we can actually say, for example, the charge line. I can call that equal to this, and I can set that equal to this, and then I can do a similar thing for I. So we have Q and I, and this is going to be X2V, and let's make this a different color just to be fancy. And then let's plot this. Let's see if this runs okay, and then we'll do some more stuff. If this runs okay, then we'll do some more kind of dressing up a little bit. All right, so now we have both of our results that are plotting, and the result gives the first line that we have here is the charge, which is the blue line. So the charge starts from 0 and it ramps up, and then it settles, and then it starts to and this is the red line is the current, and then it comes up and it settles. So this is actually the solutions to the equation, and the x-axis, of course, are just the variable of time. So let's now let's finish adding some things to make this plot a little bit more readable and user friendly. So first, for example, we can do a title, for example, and let's do we can do the Hertz experiment. This needs to be a string, by the way, so missing that. And we want to also do let's do space, and then we're going to add to that. And this is where we're going to say, actually, this will get a little bit messy, but it's just because I want to be able to, because we're going to change some of the parameters, but what we're going to do before we do that is make sure on the plot that those parameter values get shown in the title. So we're going to say R, so it's RLC circuit, so we'll say R equals, and then we'll say this is R, and then we're going to add something like this for the other two parameters for R, L, and C. Oops. And why don't I do L, and then we'll again do a similar thing for C. So whatever value when we change the C value, the capacitance, then it'll actually show, it'll display whatever the number, whatever value we set it at on our figure. So we got L, C, R. Okay, let's see if this runs without error. All right, so we got our Hertz experiment circuit model, RLC. We got the value of L, the value of R, excuse me, value of L, value of C. And then we want to add some labels, let's say, for example, for the x-axis. So we'll say, and to do that, we'll just do an X label, and that's just time. And actually by default, depending on it just depends completely on the units, but we can, for example, divide, for example, we can do it as a multiple of the period of time, and then I can, by multiplying this by 1 over TP. And that will give us units of periods. So it'll be some number of periods. So now we set 3 periods. So now we actually have 3, and that's what we expect. So that looks okay. So now let's give ourselves an X or a Y label, and we're plotting. Well, we don't. It depends on what you like to call it. Let me use some mathematics notation here, so just so you can get some play with that. So let's do it as an actual subscript, because we can do that. And I guess we'll just say QI. Okay, so now we have our solution to our circuit, the model that is basically simulating the experiment done by Hertz. We have basically an effective RLC circuit with a DC battery supply, and this instance of 0 in time is basically right when you throw the switch. There's no current, there's no charge, and as soon as that happens, there's going to be an immediate rise, and there's a time constant that determines how fast this rises, and that time constant is actually given by tau. And then the oscillations that we see here is actually controlled by the time constant we call omega, or the period, which is 2 pi over that omega. So both of those numbers play a role in the features that we see in this curve. So now we can play around with the values and see how things change. Let's say, for example, let me take the inductance up a little bit. I'm going to take the capacitance back down, and let's take the inductance up. Notice that we start to see, as we increase the inductance, we start to see more wiggle in this line. Now remember what we're looking at. We're looking at basically a kind of a dying out, or a transient. It's almost like a pulse. It's basically like a momentary time oscillation of, in this case, charge, current. But remember, these things are all coincide with an electromagnetic field. And it's these charges that are oscillating at the surface of the gap are actually oscillating at these frequencies. And this is the charge, and this is how it's varying with time. Of course, depending on the actual values of L, R, and C. But I just want to, you can see what the role of having a high inductance is. So let's continue changing that to higher and higher values. And this just helps us to understand what the physics is and why, these the inductor coils and things like that were used. It's because they actually contributed to the generation of the oscillation. You see that? So the oscillation is what gives rise to the oscillating charge, which gives rise to the electromagnetic field, even though it doesn't endure continuously. It's actually just a short-lived pulse that gets kicked out in the gap, and the gap actually, in physically what happens is the electric field actually ionizes the air. This is what causes the actual gap, that the spark, that you see in this experiment. The spark is caused from this relatively large electric field that is oscillating, and it actually ends up ionizing some things that are in the air. And the ionization of the things in the air is what causes the spark. And so the ionization process is what is visualized as the spark, but it's also associated with this electromagnetic wave, and it basically hops or jumps or propagates directly over 1.5 meters away or 1.6 meters away to the receiver, and does the kind of the same thing where the electromagnetic field, oscillates and basically does a similar thing at the receiver, and you see a spark at the receiver. But all of this is enabled by the fact that you're able to generate a short-lived oscillation. Even remind you that we don't have any AC current, no AC voltage source in this loop. There's only a DC. And for this reason is the reason why this doesn't endure. And the reason it dies out is because of the resistance in the line. As long as you have a resistance in the line, it's going to die out. And there was a large amount of resistance in this line. So if I were to, again, continue to up the resistance to some value that's much larger, you'll see that it dies out even quicker. And you can, of course, play with these numbers, and now you can see it doesn't even go up to oscillate. It dies out immediately, or fast. So this wouldn't be a sparker. This would not be a sparker if your resistance was so high compared to your inductance. So this tells us that you would need your inductance to be really, really large in comparison to all of your other parameters, so that you can really get the conditions to generate a spark. So let me take that back down, and we'll take up let's double our inductance to some value like 8, calculate the number there, and then we start to see, the oscillations appear. And the frequency of these oscillations correspond to R omega. And then the dying out of them and the time constants corresponding to how fast this dies out corresponds to tau. So we have two different time constants that are affecting the dynamics of the loop of the circuit. And so this is what the charge looks like. And the charge bottoms out here. We went back to 0.5 for the volt for the battery source. And so it's volting out at C times V. And if you recall the solution that we had, it's going to basically settle out at V times C. C is 1, so it's going to end up at 0.5. So this is just oscillating before it settles down to a DC charge on the capacitor all across the gap. And that charge is going to be a DC charge. But before it actually accumulates all of the charge, there's going to be some oscillations which are enough to actually excite this AC electromagnetic field and cause sparking in the gap. And so we now have a little bit better understanding of the discovery or the ability of Hertz to generate an electromagnetic wave in his laboratory with his setup. It actually is not super complicated if you just break it down to the simple, circuit. Of course, we say this, many hundreds of years later, but the point being that understanding circuits and circuit components like inductors, resistors, and capacitors, we can definitely calculate, and having numerical methods available to us, we can calculate solutions to problems like this pretty easily, and it gives us insight into what's going on in the physical problem. So here we have our description of the Hertz experiment, and we hopefully have some better understanding of what was going on in Hertz's experiment, where he's able to generate, why is it a pulse and not, why does it not endure indefinitely was because of the resistance in the line and the inability of this to persist indefinitely. The oscillations, to persist indefinitely because of finite resistance in the line. But why is there even AC in the line? Well, it's because the combination of the inductor and the capacitor creates a harmonic oscillator, and the harmonic oscillator causes the oscillation for the charge. Oscillations for the charge leads to oscillation for the current, and all of those things create electromagnetic waves. All right, so this is the idea behind the Hertz experiment. I hope that makes sense. And you can, hopefully you were coding along with me, and you now have this code, and you can play around with it even more and also plot these things out. That wraps up our video for today, ladies and gentlemen. Thank you for watching. Now, if you really like this video, then please consider giving it a thumbs up. If you really, really like the video, then please subscribe to our channel and stay tuned for more information and tutorials relating to learning physics, mathematics, and coding. All right? So thanks again for watching, and we'll see you the next time.